Hi, this is Mrs. Hanson, and in case you were absent or if you just felt like you needed a little more clarification on some of these no calc practices, that's what I'm going over. So this is chapter 4, no calc practice. All right, so the goal here is I wouldn't wish it upon anyone to watch this entire video, but rather I would suggest that you just scroll to the ones that you have questions about and focus on those. And for heaven's sakes, just because I explained it doesn't mean it's clear. So if you have further questions, please make sure you come talk to me or send me a text to remind or send me an email or come before school or after school and make sure you get your questions answered. Okay? Promise you'll do that. And also, the goal today, of course, is to focus on concepts and test taking tricks, but also to really focus on doing calculations without a calculator. So I hope I share some helpful tips for you. All right, let's get started. So we are happy. Okay, so I'm going to go through each one, but like I said, some of them are pretty easy. Just, fast forward till you get the ones you're interested in, to the ones that you are interested in. So number one, what is the balanced equation for this reaction? So they give you this big, long description, but truth be told, I think even without the description, you know how to do single replacement reactions. So element plus a compound. The cation is gonna hook up with the anion. So you're gonna make magnesium chloride. Just make sure you remember to balance your compounds. So magnesium 2 plus and Cl minus. Okay, so you would need 2 Cl minuses to balance out that magnesium. And then by gum, hydrogen is going to be the element that gets kicked out. Okay. And then you can come back and balance the whole thing. So we'll put a 2 right there. And now all the atoms on both sides are balanced. Good. So from the clues in the problem, the big thing that they said is that when magnesium was reactive with HCl, you made a gas and it was odorless and colorless. And chlorine is green and smells bad. In fact, it's pretty darn poisonous. So that means that's how you knew that one couldn't be right. This one, it doesn't have hydrogen. It's being diatomic, and this compound's not balanced, so it's just bad, just real bad. C is the correct answer, and D puts in both those gases, and of course, it makes no mention of that, so that guy's out too. All right, so C is the correct answer. Then let's see, number 2. Now it says identify which substance is being oxidized and which substance is being reduced. Okay, so let's see. For the upcoming chapter 4 assessment, there will not be redox. However, this one was a pretty easy one, so we'll just go through it. So an element all by itself is going to have an oxidation state of 0. Hydrogen's a +1, chlorine's a -1 to cancel out. Again, magnesium is a cation, so its cation is the oxidation state, so +2. Chlorine's a -1 still, and hydrogen element all by itself is 0. Okay, so hopefully you would see that the magnesium went from 0 to +2, so it's becoming more positive. So that must mean it is losing negative electrons. So that's your oxidation. Okay, and then the hydrogen is going from a +1 to 0. So that's reducing in positive charge, sometimes I like to say. In other words, you must be gaining electrons to go from a +1 to 0. So that is our reduction. So that would make letter C the correct answer. All right, pretty easy. All right, so let's go on to number 3. So number 3, okay, so let's see, 200 mils of 0.6 molar magnesium chloride is added to 400 mils of distilled water. Sounds like a dilution problem. So hopefully you were thinking, oh, okay, dilution. I'm going to apply the dilution formula. That would be awesome. But before you get ahead of yourself, to be honest, sometimes it's helpful just to peruse the choices because really you don't have to do any math because there is only one possible answer. So let me explain. So the whole question really is, okay, what's going to be the concentration of magnesium ions? Okay, that's an equal sign. Sorry. Bloop, 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 bloop. There we go. And then it says, what would be the concentration of the chloride ions? Okay, and if there's one thing that you feel pretty confident about is that in magnesium chloride, for however many magnesiums you have, you're going to have 2 chlorines. Okay, they have to be in a 1-to-2 ratio. So actually, the only choice that's possible is letter B because the magnesium and the chlorine are in a 1-to-2 ratio. So A, 1-to-1, not going to work. C, 1-to-1, not going to work. D, whatever the heck that is, not going to work. So if you're thinking about test-taking strategies and not having a lot of time, you just saved yourself some time there. Okay, so what do you think of that technique? Just for the fun of it, though, it is fun, isn't it? If you did want to do the calculation, it's always good practice. There's probably one common mistake. So let's see, our starting volume is 200 mils. and the starting concentration is 0.6 molar. Okay, and then, okay, what would be the new molarity of the magnesium chloride when you add 400 mils of distilled water? So the key here is just keep in mind that this volume is always the total. So if I add 400 mils of distilled water, there's already 200 mils there. So the new total is 600 mils. Okay, and that's probably the most common mistake I see students make. All right, then to solve for M2, you can divide by 600. And if you hear my cat in the background, I apologize. And we can go from there. So what would be the molarity? The new molarity of this magnesium chloride solution after diluting. So how do you do that math in your head? Well, I guess what jumps out to me is to simplify as much as possible. So I'm going to take 200 and 600, and we'll make this 100 and 300. How does that sound? Okay, or better yet, how about 1 over 3, right? Okay, so divide both by 200. Okay, so that goes in once, and 200 goes into 600, 300, 3 times. Okay, so now we basically have 1 times 0.6 over 3. So basically, what's 0.6 divided by 3? I would say that's 0.20 molar. Okay, and that would be the magnesium chloride. So that would equal the magnesium 2 plus ion. And for the chloride, of course, it would be double that. Okay, what do you think? Pretty easy? All right, good. So that was fun. We're getting into that mental math. I love it. All right, let's see what's next. So now we're going on to number 4. Ooh, this one is an interesting one. Number 4. Okay, first of all, determine the volume of distilled water that should be added to 20 mils of 12 molar HCl in order to produce 0.5 molar HCl solution. Okay, so it looks like this one sounds like another basically dilution problem. Okay, so you got your M1V1. Whoops, I'm sorry. I got to make that a little neater. Equals M2V2. So let's see what we got here. So we're looking for the volume of distilled water that should be added, okay, to 20 mils of 12 molar. Okay, so there's my molarity, 20 mils. And folks, you know what? If you're using the dilution formula, there's no reason why you can't keep things as milliliters. As long as you're consistent, milliliters is fine. Okay, and in order to prepare my new molarity, 0.500 molar, okay, and I'm looking for this volume. Okay, so all right, let's go ahead and solve this. So we're solving for V2, so I'm going to divide, whoops, that's not what I wanted. We're going to divide both sides by 0.5, like so. Divide both sides by 0.5. Okay, cancels out. So now we're looking for that new V2. Okay, again, mental math. So I'm like, ooh, basically, how can I simplify this? Okay, well, what I see is, let's see, 0.5 into 12 is basically the same as multiplying it by 2. Okay, so basically, instead of dividing by 0.5, I'm just going to multiply by 2. Does that make sense doing that? Okay, because I like multiplying a lot better than dividing. Okay, and then basically 2 times 12 is 24, or 24, okay, times 20. All right, so it looks something like that. 2 times 12 and then times 20. So that's a 0, and that's an 8, and that's 480. Okay, so my answer is 480 milliliters. All right. But great, you know what? Then you're tempted to choose choice D. But guess what? That's not the right answer, because you got to read the question real carefully. And it's even though this is a total volume, so if you want to dilute this solution, okay, and make it 0.5 molar instead of 12 molar, yes, the new total volume would be 480. But it says what volume of distilled water should be added. Well, guess what? There's 20 mils already there. Okay. So if you subtract away the 20 mils that's already there, guess what your actual answer is? That would be 460. Woohoo! Okay, so actually choice C is the correct answer. But I cannot tell you how many students chose choice D by accident. Okay, so just keep in mind, you get so excited that you see one of the answers that actually matches your work, but be careful, okay, because we always put distractors and things in there. Okay, so read the questions carefully. What do you think? Good times? All right, so that was a fun one. All right, let's see. Get rid of all this craziness. What about, this one. This one actually, I think, is probably one of the most important on this entire document. Okay, really shows that you understand, you can visualize and you understand things conceptually. Okay, now of course on the copy you're using, I did you a favor because I went ahead and counted things. Okay, and you know what? That's a technique you can use. So when you get a picture like this and you're like, oh my gosh, what is going on? There's all these circles and all these different colors, is I would tally everything up. Okay, so in this beaker, just like your copy of this no calc practice says, there's 2 lead ions. Okay, those are kind of the grayish ones. And then there's 4 nitrates. Okay, and then on this side, you basically had 5 K pluses, 5 I minuses. Okay, and that was what was in that solution. So those guys aren't present. Okay, so and then it's basically, okay, which one of these beakers best represents what this is going to look like at the end. So what jumps out to me is that, first of all, you got a double replacement reaction, right? And we made a precipitate. Okay, so if you think about the net ionic reaction, the active players here are going to be Pb2 plus 2I minus makes that precipitate, right? Okay, so of course, anytime you're given like these amounts, okay, you need to figure out which one's your limiting reactant. And I think you can do that just with the numbers. So I'm going to basically, more or less ignore the spectators, so the K plus and the nitrate, and say to myself, okay, if I have 2 Pb2 pluses and I have 5 I minuses, which one am I going to run out of first? Okay, and hopefully you can see that, gosh, I'm going to make as much lead iodide as I can. So I'm going to use both of these. Okay, so I'm going to make 2 lead iodides. And by doing that, I'm going to use 2 PBs, and then I'm going to use 4 of the iodines, right? Okay, so if you understand that, you can basically pick out the best choice below. Okay, so the limiting reactant is, here, I'll get rid of that. And can you guys actually hear the cat in the background? I'm really sorry. It's meowing like crazy. So that's a limiting reactant. Okay, so what does that mean? In solution, if you look at choice A, B, C, D, if you see any lead ions, that's a bad one, because you know that if lead is part of the limiting reactant and lead is part of the precipitate, its molarity is 0 molar. Okay, so guess what? That means this one's out, okay, because those 2 little guys are lead. And then actually D is out as well because it has that lone lead ion as well, okay? And then if you look at A and B, well, keep in mind that if lead is a limiting reactant, you used 4 I's to make all this precipitate, but you have 1 left over. So you better have an I minus left, okay? And if you look at A, I minus is basically the purple ones. There's no I minus there, okay? So that guy's out. But this one, see that little guy right there? That little tiny I minus? Okay, it's hard for me to point to it, but that right there is super important. Okay, so that's my I minus. So I got that I minus, and then if you guys continue, I kind of tallied them up for you, but you got your 5K pluses to match the original 5K pluses, and you got the 4 nitrates to match the 4 nitrates. Okay, that the spectators didn't change. And then you got your 2 leads down here locked in the precipitate. You got your 4 iodides locked in the precipitate. Everything else looks great. Okay. So that was a really great question to make sure that you can visualize these solutions. Okay. All right. What do you think? Good? That's one of my favorite questions. I really love it. Okay. Number 6. So going back to this picture that we have, what species are your spectators? Okay. And hopefully you guys decided that potassium and nitrate were the spectators. Good. All right. I couldn't tell you to do these types of problems enough. Okay. Visualizing solutions, super, 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 super important. All right. Make sure you count up the particles and just be really consistent if you are asked to do a drawing. Good. All right. I love that one. If you got questions, be sure to ask in class. Let's see what else we got here. Ooh, number 7. Ooh, that's a favorite of mine too. So this is number 7. Okay, so it says, what is the molarity of a solution containing ClO2 minus if, so what I like to do, is you got your reaction. I'm just going to kind of blow it up a little bit, just recopying it, okay? And the funny thing is I did the reactants. I don't even care about the products, okay? They're not really all that important, okay? So I go through and I say, what is the molarity of a solution containing ClO2 minus? So I'm looking for the molarity. If 15 milliliters of the solution is needed to react completely with 20 mils of 0.2 molar KMnO4, okay? And notice I added that K. Of course, in yours, there's no K there because, you see what I mean right there? Because you probably guessed potassium is a spectator. So I'll go ahead and, oh, you know what? That's a 4 right there. Let me make that a little clearer. There we go. Okay, so MnO4 minus is the same thing as potassium MnO4, right? K is just a spectator. All right, so here's our problem. I mean, classic titration problem, meaning that you got your known, you got the molarity and the volume, so you can figure out the moles of this guy, and then you can use the balanced equation and the mole ratios to figure out the moles of this guy. And then you can solve for whatever it asks for. So in this case, it's asking for that molarity. Well, let's go ahead and give it a whirl. It's a little tough to do without a calculator. All right, so I'm going to go ahead and take my volume. I converted it to liters. Okay, and then I'm going to use, whoops, clean that up a little bit. Okay, then I'm going to use the molarity. Whoops, as a conversion factor. Okay, so that's basically my MnO4 minus. And then I'm just going to keep going. Okay, so this is the really important part. This is where your ratio is. For every 1 mole MnO4 minus, okay, I'm going to need 3 moles, okay, of ClO2 minus. Okay, and I'll tell you what, from all the times I've seen students work through this problem, that is the part that they forget. So just remember, it's a titration, so it's based on stoichiometry. Okay, so that mole ratio is how you go from one substance to the substance you're interested in. All right, so now, without a calculator. So, I like to map out as much of the work as I can and then look for places to simplify. So what I see is, well, I think I can multiply those, okay? So let's see, 0.20, whoops, let me make that look a little nicer. 0.20 times 0.02, okay? Doesn't matter which order you do it in, but if you're multiplying basically one number by another number, this is easy. So 2 times 0 is 0, 2 times 2 is 4, okay? And then how many decimals, okay? So let's see, 1, 2, 3, 4. So 1, 2, 3, 4. Put the decimal place in. Okay, so is that a technique that you guys remember? You know what? I like that so well. I'm going to do it one more time just to make sure that you're really following. Okay, so, and you know what? I'm going to, just for the fun of it, I'm going to do it the opposite way. So let's say you took 0.02 and you multiplied it by 0.2. It doesn't matter. 2 times 2 is 4. 2 times 0 is 0. 2 times 0 is 0. Okay, now how many decimals are in this problem? Let's see, we got 1 here, 2, 3. So I'm going to start at the far right. 1, 2, 3. Put my decimal place. Got the same answer, 0.004. Is that pretty cool? You guys remember how to do that? Okay, so long story short, we did that hopefully simple math. Okay, and now we're looking at this being 0.004, right? Okay, and then I see a really nice way to simplify because this 4 down here, boom, will cancel out with this 4. So now that's basically a 1. So it's 0.001. And then I can multiply it by 3. So it's 0.003 moles of ClO2 minus. What do you think? Okay, so that's some tricks, right? So it's just whatever jumps out as the easiest numbers to manipulate, start there. Okay, and there's lots of other ways to do it, but that's what jumped out to me. All right, now what was the question? It said, what is the molarity of the solution? Okay, so molarity of ClO2 minus. Okay, so let's see, I'm going to take that mole value I just calculated. And then, okay, now here's always the age-old question. What volume do you put on the bottom here? So because for some problems, we add together the total volume. Like we take 20 mils plus 15 mils. Okay, but for other problems, we don't do that. So what's the right answer here? Okay, so this is the best piece of advice I can give you. For this problem, it's asking what is the molarity of the solution that you started with, the ClO2 minus, okay? If it wants you to add those two volumes together, I promise you, somehow in the problem, it's going to say, oh, what would be the ion concentration of that at the end of the reaction, after the solutions were mixed? In the final product mixture, there will be something about the language that tells you that it wants the ion concentration after everything's been done. For titrations, it's usually not the case, okay? Because you're basically trying to figure out what was the molarity of that original solution. So that many moles, 0.003 moles, was spread over what volume, okay? And you have to go back to the original given volume, so which was 0.015 if you convert it to liters. Does that make sense? So sometimes students blame the math and they say that's why they get problems like this wrong. But sometimes it's the concepts, like, you added the volumes together instead of just using 15 mils, okay? Now, last but not least, boy, if there's an issue students have with mental math, multiplying is hard enough, but dividing and figuring out where to put the decimals really messes with students. So for this, being able to calculate this right here can be pretty challenging for students. So I'll show you a technique that I like. So, okay, so I know you guys might not believe it at first, but I'm going to kick it back old school and go to dimensional analysis. Okay, just hear me out on this. So for 0.003, if I put that in not dimensional analysis, scientific notation. If I put it in scientific notation, that number, 0.003, is 3 times 10 to the minus 3. Do you agree? Okay, and because this is a multiple choice and we're kind of in a hurry, right, I left off the times 10, okay? So it's 3 times 10 to the negative third. And then on the bottom, let's see, I'm going to move the decimal place 2 spots to get 1.5, okay, times 10, and I moved the decimal place over 2 spots to the minus 2. Now, that's actually some math I can do, because how many times does 1.5 go into 3? It goes in twice, okay? Easy. And then if you remember from your basic math, what do you do when you divide exponents? Hopefully you remember that you subtract them. So minus 3 minus a minus 2 looks something like that. So of course those minuses are going to cancel, or going to cancel out like so. So that's what you're looking at. So really what that number ends up being, if I can make a little more space here, ends up being 2 to the minus 1. Okay, and if you convert that back to a normal number, you're basically moving the decimal place over 1 spot, whoop, like this. Okay, so your answer, believe it or not, is 0.2. Okay, and that would be the molarity of this solution. So that's kind of a lot of work to get there. Kind of like thinking about test taking strategies, looking at your choices. If you got all the way to this part and you had your choices, I mean, I would simply say, well, gosh, 1.5 goes into 3 twice. I would know that there's a 2 in my answer. So I would pick B, and I wouldn't even worry about necessarily where the decimal place is, okay? Because the other numbers just wouldn't match up at all, okay? So, hey, when it's multiple choice time and you're taking a test, you are more than encouraged to do those kind of shortcuts, okay? But if you ever really need to know what that number is, I encourage you guys to try that scientific notation technique, all right? Whew, that was kind of a long explanation for that one. Okay, so I'm going to go ahead and erase that. Let's see if I didn't melt your brains on that one. We'll try another one. All right, how about number 8? Okay, so this one, there's something I really, really, really love about number 8. It says the sample of calcium hydroxide is titrated with HCl. Folks, there's no reaction written. You have to write one. Okay, I will promise you, you won't get these right if you don't write out the reaction. So calcium hydroxide reacts with HCl. Classic double replacement, okay, neutralization. So we're going to make calcium chloride. It's a 2 plus and a Cl minus, so you had to balance it out, and water. And I like to write water as HOH, okay, and neutralization reactions makes it a lot easier to balance. So now I come through and I say, okay, well, if I got 2 OHs here, I'm going to put a 2 in front, 2 OHs. Now I got 2 H's. 1 H, so I put a 2 in front, 2 Cls, and now it's balanced, okay? If you didn't balance that, you wouldn't know that you got this really important 2-to-1 ratio, okay, that you're going to have to manipulate. All right, now this problem's pretty easy, okay? So it says you got a 25 mil sample, okay, of 0.120 molar. Calcium hydroxide is titrated with a 0.15 molar HCl solution. What volume of HCl is needed to completely neutralize the calcium hydroxide? Okay, so that's kind of what we're looking at. All right, so okay, pretty straightforward. So let's see. I'm going to go ahead and start this one up here. So again, I got my molarity and my volume of my known. Okay, and then I'm going to get the moles and then use the mole ratio to get to the moles of what I'm interested in, and then I can come back and solve for that volume. All right, let's do it. So let's see, 0.025 liters, okay, for the volume. Okay, and then 0.120 moles per liter using that molarity. Okay, and that's for the calcium hydroxide. Okay, and then, oh, here's the money step right here. For every 1 mole of calcium hydroxide, you're gonna need 2 moles of HCl. Okay, and I'm willing to bet that if you got this one wrong, it's not necessarily the mental math, but I'm guessing that you might not have utilized that ratio. And it might be because you didn't write out the balanced equation. So please, 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 please promise me that if a reaction is described, you got to write out the reaction yourself. Okay, so we got that. All right, so now we can start talking about doing that mental math. So I'm just going to give myself a little more room here. All right, let's see what kind of jumps out, like what I can put together. So I see that maybe I could do 2 times 0.025 because that's pretty easy. Okay, so that would be 0.05. Okay, and then times 0.120. So it's basically, to me, that kind of looks almost like 50% of 12, right? So, and if you didn't know exactly where the decimal was, this is an easy one. Anytime you have like one number multiplied by anything, it's super easy. So I'm going to go ahead and work that out. So 0.12 times 0.05. Okay, 5 times 0 is 0. 5 times 2 is 10. Carry the 1. 5, 6. Okay, and then we don't care about the zeros. So now how many decimal places? 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So it looks like the answer for that part is going to be 0.006. What do you think? Okay. All right, so that's my moles of HCl. Okay, so what did you think of that? All right, now what the heck's it asking for? So it says, let's see, bloop, 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 what volume of HCl is needed to completely neutralize? Okay, so we need a volume. Okay, so now we say, well, I guess I'm going to use the molarity formula. Okay, so molarity, of course, was given for the HCl solution. Okay, it was this guy right here. So I have a 0.150 molar solution and then equals moles per liter. So I have the moles, but I'm looking for the liters. Okay, so we'll just call that X. Okay, so that's what we're solving for right there. Okay, so molarity equals moles per liter, right? So we got the moles, we got the molarity. Okay, we're looking for the volume. So, of course, I'm kind of preferential to cross multiplying. So I'm going to do something like that. Okay, so if I'm solving for X, okay, then I'm going to multiply these two. So 0.006. Okay, and then I'm going to divide it by what's connected to the variable. So I'm going to divide it by 0.150. Okay, hopefully that's what you like to do. Okay, so cross multiplying I think is really easy there. Okay, and now you got some math to do. So you're like, ooh, those decimals, those rascally decimals. All right, and I'm telling you, okay, try that scientific notation trick. Okay, so I'm going to say to myself, okay, 6, 1, 2, 3, so the minus third divided by, and then I'm going to move this over one spot. Okay, 1.5 to the minus 1. Well, now that's math I can do. How many times is 1.5 going to 6? Okay, and hopefully you're like screaming at the top of your lungs that goes in 4 times. And then minus 3 minus a minus 1. Okay, so then those become positives. Okay, so basically what we're looking at is 4 to the minus 2. Okay, so then what does that actually mean? You're going to take your 4, put the decimal there, 1, 2. So your answer is 0.04 liters, okay, which they gave you answers in milliliters, so you'd just multiply that by 1,000. So then you'd go back, 1, 2, 3, so that's going to be 40 milliliters. Whew. Okay, and that would be choice B. All right, so a couple things right there. I think what was tricky about it is, first of all, I had to get that mole ratio. Okay, yes, folks, I think you can be asked to multiply like basically one digit by a bunch of other digits. Okay, you can do that. Okay, and then when it comes to solving for the volume, which was on the bottom, definitely a good technique to cross multiply. Okay, so you multiply what's away from the variable, so 0.006 times 1, and then divide by what's connected to the variable. So divide by that 0.150, okay? And then when it comes to dividing, try that little scientific notation trick, okay? And it, I think, makes it a lot easier. Okay, well, that was a fun one. Whew, that was a pretty hard one. A lot involved there, okay? All right, let's see. We'll just move on here. All right, we got away from the math for a little bit. Okay, so number 9, it says basically you got this reaction going on and you made it precipitate. Okay, so what could that precipitate be? Okay, and hopefully you would see that you're basically taking Ag plus, and right here, those little gray guys, and you're going to react it with the Cl minus, which is those nice, pretty green guys. Okay, so 3 Ag pluses, 3 Cl minuses made your 3 AgCls down here, and your nitrates, okay, and whatever the other spectator, the K plus, are still just floating around, okay. The spectators are definitely potassium and nitrate, okay, good. 11, honestly, that's not going to be on your assessment, but it is good to practice. So all of them have nitrogen in it, and guess what? Nitrogen can be lots of different oxidation states. So I would always start with the other atom, okay, so N bonded to O, let's see, oxygen's probably a -2, so nitrogen's a +2. NO2, of course, now you got 2 nitrogens, so that's a -4, so nitrogen's a +4. Good. And then N2O, oxygen's a -2, so you got a +2 on the nitrogen, so each nitrogen is a +1. All right, and last but not least, N2O5, -2 on the oxygen, so that's a -10. It's a +10 on the ends, spread over 2 nitrogens, so that makes each nitrogen a 5. That, my friends, is the biggest oxidation state. So D is the correct answer. All right, so those were pretty easy. Let's continue on. So number 12, it says a 1 molar solution of table salt is considered to be 1 molar Na plus and 1 molar Cl minus. That means that sodium chloride is a strong electrolyte because it broke up all the way, 100%, into Na plus and Cl minus. Good. Hopefully that was a pretty easy one. Okay. A weak electrolyte would have produced some Na plus and some Cl minus, but not 100%. And a non-electrolyte would produce no ions. Okay. Good. And a strong acid is going to behave like a strong electrolyte, but of course, sodium chloride does not fit that description of an acid. All right. So that was an easy one. Let's see what else we got. How about 13? All right, so it says consider 100 mils of a 1 molar sodium chloride solution in a beaker. After several days, you test the solution and find that it has a concentration of 1.33. How much water must have evaporated? Okay, so with this one, it's basically just using this molarity formula, okay, in a pretty creative way. Okay, so when you first started, okay, you had 0.1 liters, 100 mils, okay, and it was 1 molar. So if you calculate the moles, okay, you had basically 0.1 moles of sodium chloride, okay? And guess what? When this was given some time and some of the water evaporated, you still have those 0.1 moles of NaCl there, okay? So now the matter is that some of the water left, so you have a new molarity, okay? So now you say, okay, well, now I got this new molarity, but my moles is still the same. Okay, so what must that volume have gone down to? Okay, so that's kind of what you're looking at here. So it's another one of those problems where you got volume on the bottom. Okay, so I like to cross multiply. So again, to solve for this new volume, I'm going to multiply what's away from the variable. So I got 0.1, 1 times 0.1, and then divide by what's connected to the variable. Okay, so divide by that 1.33. Whoops, that looks a little ugly. Okay, so 1.33. Sorry, I'm trying to make that look nice. It's 0.1 divided by 1.33. Okay, so now what do you do with that? So what is 0.1 divided by 1.33? Okay, and hopefully as best as you can estimate, that would be about 0.075 liters or 75 milliliters. Okay, and be careful because that might have prompted you to pick C as your answer. But mind you, you got to read the question carefully because that would just be your new volume after some water had evaporated. And the question said how much water must have evaporated. So you have to take that 100 mils that you started with and minus the 75 mils that you just calculated. And that, my friends, is how you got 25 as your answer. Okay, so that's a pretty tricky one, right? Just manipulating that molarity formula. Okay. All righty, moving right along. So number 14. Okay, 14, really important question. Okay, it says calculate the concentration of chloride ions, okay, when 200 mils of 1 molar is mixed with 300 mils of 1 molar magnesium chloride. Okay, so the key here is we can get the moles of both. So for sodium chloride, it's 0.2 liters times 1 molar, okay, and that's 0.2 moles, right? But the key is do we want NaCl or Cl minus? Okay, so for every 1 mole of sodium chloride, you'd also get 1 mole of Cl minus. So it's also going to equal 0.2 moles of Cl minus. Okay, now here's where it gets interesting. For the magnesium chloride, you had 300 mils, okay, and times 1 molar. So you can multiply those and get 0.3 moles of magnesium chloride. Okay, so the question is how many chlorides do you have? For every 1 magnesium chloride, you get 2 Cls. So you'd have to double that to get 0.6 moles. Okay, so I think that right there is kind of the key, is remembering to multiply this by 2 to get the chloride, not just the magnesium chloride. Okay, and when I said concentration, what I actually meant is these were the mole values, okay, because we're not done yet. So now that we got moles of chlorine here and we got moles of chlorine here, guess what we're going to do? Okay, so we're going to add those two guys together. Okay, so 0.6 plus 0.2 is 0.8 moles. Okay, and by the way, that right there is a Cl minus, not a plus, sorry. There we go. Does that look better? And then we're going to take that total moles, okay, of chloride, and we're going to put it over the total volume. So the total volume was these two numbers added, okay, which is 0.5. Okay, so 0.8 divided by 0.5. Okay, hopefully you guys can come up. And this one's a little tricky because you got B and C, 1.4 and 1.6. Okay, so hopefully, sometimes you just got to kick it back old school and do some long division. Okay, 0.5 into 0.8. So I'm going to carry that decimal. It goes once. Okay, and then that's 0.5. Okay, then that becomes 0.3, and then bring that 0 down. How many times does 5 go into 30? And that's 6. Okay, so hold on. I kind of did that a little bit funny, so let me clean that up because I had decimals kind of flying all over the place. Okay, and I also don't like that red. I just don't like it. Let me try that again. So 0.8 divided by 0.5. Your first step is you really do have to move that decimal. So I'm going to move because you need like a whole number there. So I'm going to move that decimal place over, but what I do to the 0.5, I have to do to the 0.8. Okay, so that moves like so. Okay, and then there's where my decimal is going to be. Okay, so I'm trying to make a decimal right there. Okay, so that's going to be 0. Okay, and then 5 into 80. Okay, hold on. Hold the presses. Okay, so it's 0.8. Okay, one more time. Let me make this nice and neat. 0.5 divided by 0.8. First thing, move the decimal. Move the decimal. So now the decimal's right there. Okay? Okay, and then we'll add a 0 if we need to. So then how many times does 5 go into 8? Once. 1 times 5. So we got rid of this guy. Okay, it's just a 5. 1 times 5 is 5. Okay, subtract from 8. That's 3. Bring down that 0. Now we got 30. How many times does 5 go into 30? 6. Okay? Whew. Sorry. Okay, so 1.6 is your best answer. And folks, with a little practice, I promise you that basic division, basic multiplication will come back to you. Okay, so don't hesitate to kind of go old school like that. Good? Alrighty. So that, my friends, was number 14. The answer is C. Okay. Ooh, 15. I like 15 a lot. I like 15 because it reminds me of number 8. Okay, and the key with number 8 is that a reaction is being described. what volume of sulfuric acid is required to neutralize potassium hydroxide. So you have to write out a balanced equation. So I'm going to do just that. H2SO4 plus potassium hydroxide. Okay, so the H is going to go with the OH. We're going to make water. And then our salt is going to be K. And since K is a plus and sulfate's a 2 minus, we need 2 Ks to balance out that sulfate. Okay, and then we'll balance this whole rascally thing. So we got 2 H's here, but 1 H here, so I put a 2 in front. 2 OH's, only have 1 OH here, so I put a 2 in front. 2 K's, 2 K's, 1 sulfate, 1 sulfate. Okay, so if you didn't recognize this 2-to-1 ratio, you'd be hard-pressed to get this one right. So it says what volume of 0.2 molar sulfuric acid is required, and we're looking for the volume, is required to neutralize 800 mils, okay, of 0.1 molar KOH. Okay, so you guys, I think you're starting to see the trend here. So you got a molarity and a volume, so you got your known. Okay, once you get the moles of known, then you can calculate moles of unknown, and then you can answer the question, which is solve for the volume. So let's do that. Let's see here. So I'm going to go ahead and convert my liters, my milliliters to liters. Okay, I'm going to multiply by the molarity. Moles per 1 liter, and that's for my KOH. Okay, and then for 2 moles KOH, you're going to neutralize 1 mole sulfuric acid. Okay, and I'm willing to bet that if anybody makes a mistake on it, it's probably not having that mole ratio, okay, which comes from not having the balanced equation. So important, okay? Now you can think of some ways to simplify. So what jumps out to me is I see, oh, okay, well, looks like 2 can go into 0.8, like, so this end up being what, 0.4? Okay, and then 0.4 times 0.1 looks like we're looking at 0.04. Okay, 0.04 moles. All right. Now that I got the moles of what I'm interested in, now I can go ahead and solve for that volume. Okay, so again, we did one very similar. Okay, let's see if you guys can get this right. So let's see, the molarity was 0.2 molar, right? And we got the moles, and we're looking for that volume, right? Okay, so I'm going to go ahead and cross multiply. Okay, so to solve for that volume, I'm basically going to take what's away from the variable, 0.04, and divide it by 0.2. Okay, now you guys know, 2 goes into 4 like twice. So you kind of know that your answer is going to be, have a 2 in it. So that probably would let you pick A as your answer. Okay, but you can always try that method we talked about. So let's see, 4 times 10 to the minus 3, over 2 times 10 to the minus 1. So again, 2 goes into 4 twice, and then it's minus 3 minus a minus 1. So those end up turning to positive, and again, we're dealing with 2 to the minus 2. Okay, and 2 to the minus 2. Whoops, you know what? I added an extra 0. I'm sorry. So we'll get rid of one of those, and this turns into times 10 to the minus 2. Sorry about that. Good. Okay, so that ends up being 2 times 10 to the minus 1. Okay, which means if you put your decimal place right there, we're going to move over 1 spot. So your answer is 0.2. Okay, and that's 0.2 liters. So multiply it by 1,000, or it would be 200 milliliters. Okay? Alrighty, so I'm hoping that you guys are seeing some patterns, right? Some really good opportunities to practice this, okay? So the answer ends up being choice A. All right, good. What do you think? Okay, so let's see. I think we got 2 more to go. Now, these were some interesting questions, okay? And I think I probably went over these in class, but they're kind of fun, right? So I think what was unique about them is we never had 2 precipitates. So this guy was a precipitate and this guy was a precipitate. Okay, so how do we handle that? Well, guess what? It says after the reaction has gone to completion, what ions remain in solution? So it's basically saying what ions don't end up being totally locked in the precipitate, what ions don't end up being 0 molar. In other words, what ions are left over. So I think at the heart of this question is you got to figure out the limiting reactant. Okay, so going back up to the numbers, you had 20 mils of 1 molar and 50 mils of 1 molar. So if I multiply the molarity times the volume, then this would be 0.02 moles, and this would be 0.05 moles. Okay, and I think, if it was a short answer question, you'd have to justify which was the limiting reactant. But I think with this one, you can say to yourself, gosh, every time I run this reaction, I need 3 of these for every one of these. So I'm going to run out of that TS2 first. Okay, so this guy is a limiting reactant. Okay, and if you're not convinced, be sure to ask me. I'd love to talk to you, give you some different ways to look at it. So if that's the one I'm going to run out of, okay, then what does that mean about the T ions? Looks like T plus 2, I guess. And what does that mean about the S minus 1 ions? That's a 1, actually. Okay. Well, gosh, if T is part of the limiting reactant, okay, and it's part of the precipitate over here, then its ion concentration will be 0 molar. It's totally going to be locked up in the precipitate. Same thing with the S. If it's part of the limiting reactant and it's part of the precipitate, then its ion concentration will be 0 molar. Just like we've done in normal problems with just one precipitate. So nothing's changed. Okay, so the T and the S, 0 molar, none is left in solution because they're both locked up in the precipitates. All right, so what does that mean? It looks like M and R are going to be the leftover ones. Okay, so they're part in the precipitates, but they're also part left over. So it says basically what ions would remain in solution, definitely M and R. Okay. All right. So now that we got that figured out, now 17 says after the reaction has gone to completion, what is the number of moles of ions that appears in the lowest concentration of the solution? So that's a little bit tricky. It's either M ions or R ions, but which one's going to be in a lower concentration? Well, you start off with the same amount of them, but remember, for every one M2R3, you get 2 M's and you get 3 R's. Well, truth be told, which one do you just have less of? Okay, 2 M's versus 3 R's, you have less M. So when you come over to the product side, they're being used in the exact same ratio. 2 M's are being made for 3 R's. So that's kind of not going to affect anything. So I would say what you'd want to know is less M to start with means that you're going to have less M at the end. Okay. So then for that problem, we're going to focus on just the M. Okay. And basically I'm trying to figure out the leftover. So it's the same old 4 steps. So it's M, and I guess that would be a plus 3 ion. M plus 3 available. Okay. M plus 3 used, meaning locked in precipitate, and then subtract to figure out what's left over. Okay, and then the 4th step is to figure out the molarity, but for this problem, it asks for the moles of M left over. Okay, so we don't have to do all 4 steps. All right, so let's just do that. So let's see, to figure out the M available, do I start with the limiting reactant, or do I start with the source of the M? Okay, and I would say to figure out the M3 plus available in the first place, I'm going to start off with the source. So I'm going to start off with the 0.020 moles of M2R3. And then for every 1 mole of M2R3, you're going to get 2 moles of M. Okay, so I basically just double that number. 0.040 moles of M is available. Okay, all right. And then I say to myself, okay, well, how much M plus 3 is used? So that I would start with the limiting reactant. So I'm going to start with the 0.05 moles of TS2 and say for every 3 moles of TS2, I'm going to need 1 mole of M2R3. Okay, but I don't really care about M2R3, so I'm going to go one step further. Okay, for every 1 mole of M2R3, I'm actually going to get 2 moles, or I'm going to need 2 moles of M. Okay. So basically, what is that? 2 times 0.05, which is 0.1, divided by 3. So that sounds like about 0.033 repeating, right? Moles of M in the precipitate. Okay, so you guys know what to do. So now how much is left over? We got what was available and we got what was locked in the precipitate, so we subtract those numbers. So 0.04 minus 0.03 is, if I subtract those, 0.007, okay? And that's moles of M that would, whoa, I didn't expect that. Okay, that is moles of M that would still be floating around in the solution. Okay, so that was kind of a tough one to do, just without, not so much without a calculator, but just it's a lot of steps to get to a final answer. So if you were strapped for time, that would have been a great one to skip. But for now, you should be getting really, 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 really good at those steps of figuring out the leftover ion. How much is available, how much was used, locked in the precipitate from the limiting reactant, subtract. And then if you need to get the molarity, you could put it over the total volume if you needed to. All right, so that was number 17, and I believe we are done. So hopefully you found something valuable out of this video, whatever ones you watched. Please don't hesitate to ask me questions in class. All right, thank you very much. Have a great day.